Hello physics students. In the last video, I went over some key facts of conductors or metals in static equilibrium. Before I go on with this video, I'd like to review some of the key facts that we talked about. So no matter the shape of the metal, it's an equipotential as long as it's in static equilibrium, meaning it's not connected to any kind of battery forcing current through it. So you dump charge on, then this will quickly become an equipotential. What that means is that the electric field inside the metal is everywhere zero. If there were an electric field in the metal, the electrons would quickly move around on the surface to negate that or make that electric field zero. And so then when I integrate between any 2 points inside the metal, I get zero because I'm integrating zero over that path. The other thing that's true, since this is an equipotential, is the electric field, the charge can only exist on the outside. All excess charge quickly rushes to the surface and spreads out, not necessarily in an even fashion. But no excess charge could be inside because it would repel to the outside. So there's another fact. And then another fact. The surface is also an equipotential. That means the electric field only exists along the surface and it must be perpendicular everywhere to the surface. If it were not perpendicular, as we're integrating along that surface, there'd be a component along that surface and we get a voltage between 2 points on the surface, no longer an equipotential. So the electric field only on the surface points directly perpendicular to the surface, charge is only on the surface, electric field is zero everywhere inside the metal. And that's true, like I said, for any shaped metal, even this penny here, okay? So that would also be true, those facts. If you have a hollow metal, like this, there's the cavity in here, the electric field is zero in that cavity, because again, the charge moves around to make the electric field zero everywhere inside, unless you put an isolated charge in the middle, like a proton or an electron hanging in space here, it would then have an electric field around it. That's the only way. So these are the facts about electric fields around and conductors in static equilibrium. What I'm going to do now is use these two metal spheres. This is called a Van de Graaff generator, to demonstrate those principles in action in pretty dramatic form. So you've probably seen this already, but it's fun watching it again. So here we go. I'll turn this on, and there's a rubber belt that's going up into this outer metal, and you may not be able to see that. And then what happens is it's charging this conductor on the outside, and then it's creating little lightning bolts. The lightning bolts are going into this conductor over here, and you can't see it because it's off the camera view. There's a wire that runs to a sink here. When I zoom out later, you'll see the wire connected to the sink. The reason why is the wire connected to the sink is what we call a ground. The metal pipes literally run into the ground, into earth, so that the excess charge of this Van de Graaff can go into here and then go into the earth and neutralize. So let's watch these little lightning bolts in action, and to increase the dramatic effect, what I'm going to do is turn out the lights and hopefully we see a nice little display. I'll let it run for a while. It's nice to watch. Nice one. Some of the sparks are really beautiful. Van de Graaff. While this is a fun little toy that we could play with and generate sparks and do all kinds of fun stuff with, we do use it in this class to study our physics and understand more about conductors in static equilibrium. So what we're going to do is I'm going to describe and explain how this even works in the first place. Because the sparks were jumping electricity, electrons between these metals through air in between. And normally air does not conduct. Okay? So we're going to answer the question, why does the air suddenly conduct electricity? Like, for example, if I put my finger next to an outlet, I don't get electrocuted unless I stick a conductor like a paper clip into the outlet. Then I get electrocuted. Air, I could put my hand in, electricity doesn't jump through the air. Why does it jump through the air here? And going back a step before that spark even occurs, how does this even work? How does it generate enough electricity to shoot little miniature lightning bolts? So that's what we're going to learn next. Let me just get these out of the way. Don't worry, they'll come back. Charging a Van de Graaff generator. This is going to explain how it happens. So before I explain and go into the explanation, I want to first point out something, that this sphere is hollow and comes apart. The inside's very interesting. You could see the rubber belt in here coming up through the plastic here into the conductor. And then there's a pulley up here, but also a metal screen right here. Like the kind of screen you put on windows to keep insects out. And that is near the belt and connected to this inner surface with some copper wires. Absolutely critical to the working of the Van de Graaff generator. Underneath, inside this base, so I paused because I decided that after showing you the brush here, that screen, I wanted to show you the brush in the bottom of the Van de Graaff. So I took it apart, I took the base off, and you could see that there is also a screen here, a brush, and the belt is right here on this electric motor that wheels it around. So there are these two brushes, and then the belt moving between them. And we're going to see how that creates a charge on the Van de Graaff. So, we can get these out of the way again. So it's kind of like a little story of what happens to the charge. So you got this belt running, you see these arrows here. And what happens is step one, brush one down here, puts electrons onto the belt. And the belt carries these electrons up. And as the electrons approach the sphere, because it's negative, as it's charging, they're repelled away from the sphere. So they cannot jump on the outside. Okay, so it's kind of like, you know, electrons, if you could think of them as like having people qualities, then you would say they're like very antisocial. You let two of them go, they're going to race off to infinity to get as far away from each other as possible. So they don't want to be near each other because they repel. So this electron will not jump on the outside of the sphere because there's already a lot of electrons there, doesn't want to be near them. But what happens is it comes inside this sphere up here, and the electric field here is 0. And so because the electric field is 0, then step 3, the electron jumps off the belt, because see here it's next to other electrons on the belt, so it wants to get away from them, and it goes, hey, well, why don't I go here where the electric field is pointing, so the electric field is pointing toward these electrons in here, so it's going to go in the opposite direction. So it jumps on this brush to get away from the electrons on the belt. Now, once it's here, the electron, step 4, on the brush number 2, migrates to the outside of the shell, because it's to get away from these other electrons here. So it's going further, trying to get further and further away. And then what happens is it comes from the inside to the outer surface. In a sense, it's tricked to a place of a lot of electrons. So again, if we could do this sort of personification of electrons, let's suppose there's 3 people in here and they behave like electrons. They want to get away from each other as far as possible. They're crashing into the walls, trying to get out. And then I open the door and I say, hey, go out in the hall because there's no one out there. And you look, the people look and they see there's no one, they can't see anyone out in the hall. They go through the door, around the corner, and the hallway's packed with people. They were tricked into a place, going into a place where there are a lot of electrons. Essentially, that's what happens with the Van de Graaff generator in the operation of this belt in these steps. Now, that's how it accumulates a charge. But then how does that charge go through air, which normally does not conduct electricity? So, why does this spark occur? Air is usually an insulator. So what I have here is the Van de Graaff generator building up this negative charge. And what happens is this other conductor through wires connected to the earth, as I mentioned, connected to the sink. And so the electrons, some of them in this metal, go into the earth, leaving it positive. So we've got this sort of a dipole, we would call it, and the electric field points in this direction towards the negative Van de Graaff. Now, the air is made of atoms which have protons and electrons. The electrons are orbiting around the protons. The protons in the atom are attracted to this negative Van de Graaff generator. They feel a force like this. While the electrons are repelled away from this Van de Graaff generator, they feel a force like this. So, the F on the proton pulls the proton toward the Van de Graaff. F on the electron pushes the electron away from the Van de Graaff. The F net is 0 on the air molecule. The analogy would be like this. I'm standing on a skateboard and people are trying to move me. One person pulls me with 1 Newton this way, another pulls me with 1 Newton this way. I'm going to stay at rest, right? 1 Newton, 1 Newton. So they pull harder. 2 Newtons, 2 Newtons. Why do they pull harder? Well, the Van de Graaff keeps building up charge, making more electric field, making these forces larger. So 2 Newtons, 2 Newtons, I'm still at rest, right? No net force. So the Van de Graaff builds up charge, 3 Newtons, 3 Newtons. Okay, I'm still at rest. Keep going. 1 million Newtons, 1 million Newtons. What's going to happen to me? Split apart. And that's what happens to the air molecule. As the charge increases on the Van de Graaff generator, the F's increase also. Eventually the atom breaks, rips apart. The word we use for that, the scientific word, is ionizing. So it ionizes. And then there's a spark. Why is there a spark? Because this electron's now free of the atom. It's not locked in, so it shoots away and sparks into this. And so we get a discharge. The air becomes conductive. Now, the approximate electric field value at which air breaks apart or ionizes is 3 times 10 to the 6 newtons per coulomb. Okay, so that is, you could find that in our textbook in a table on page 732. So here's our textbook, right? And if you turn to page 732, there's a table here, and you can see that what we have here is a column called dielectric strength. That's what we call the breakdown voltage. And at the top, you see 3 for air, and that means 3 kilovolts per millimeter, which is basically 3 times 10 to the 6th. Okay, this table is limited. There are a lot of blanks. In another book, there's another table, this book by Survey, Physics, okay? And this is a little bit more complete, kind of interesting, because you see here that one of the entries is rubber, right here where my finger is. And if you go over the breakdown voltage, I think it's 12 times 10 to the 6th if my eyes are correct. So even rubber will have sparks going through, could have sparks going through it eventually. People think rubber always insulates, but what we know is if the electric field gets large enough, even the rubber atoms break apart and you get a spark through the rubber, okay? Now, all very interesting, but what I want to do is do something even more interesting. A calculation, a physics calculation. You might say, come on, that's not going to be interesting. Well, I don't know, maybe you'll find it interesting. I find it interesting. Okay, so if we know that this is the electric field that it takes for the Van de Graaff to create a spark? We could calculate the charge because we know the equation between electric field and charge. So, charge on Van de Graaff. E for any sphere, we could use Gauss's law, or we could just go back to the first unit here when we were studying point charges, is this. And if I want to solve for charge, Q is ER squared over Coulomb's constant. Oops, I forgot the Q. Q equals let me plug in that data for the Van de Graaff to see how much charge it achieves by when the spark occurs. So the electric field where the spark occurs builds up to 3 times 10 to the 6 newtons per coulomb. What's the radius of the Van de Graaff generator? Well, I could get a meter stick here, and I'm seeing about 12 centimeters, 24.5 centimeters. Let's just say 24 centimeters diameter, which would make a 12 centimeter, half of 24, radius. So 0.12 meters. All over Coulomb's constant. And what I get, oh, another mistake. Q. I apologize for that. And if I punch that in the calculator, I get Q equal to 4.8 times 10 to the minus 6 coulombs. When the charge reaches this, and it's negative because, you know, Van de Graaff's building up electrons, boom, spark. Now, let's do something else. Let's calculate the voltage achieved by the Van de Graaff. Because if I know the charge in the radius, the voltage at a surface of the sphere is kq over r. 9 times 10 to the 9. The charge here and the radius we said was 0.12. Punch that on a calculator. And what we get, the voltage of the Van de Graaff at discharged, 360? No, 360,000 volts. 360,000 volts. So let me pause and give you a chance to copy this down. So quite remarkable. Let me just give you some other voltages. The wall voltage is 120. If I stick a butter knife into the outlet, everyone knows that could be fatal, right? The wires that run in a neighborhood are typically 220 volts from one conductor to the other, going from house to house. Grab those. Everyone knows you go on a telephone pole, climb, grab them, you're going to kill you. 220 is fatal. Okay? And voltages can go higher in some neighborhoods, some power lines that are like feeder power lines. 12,000 volts, also fatal. And this little Van de Graaff, 360,000 volts. Okay? Now, I'm going to reset up this Van de Graaff generator, put it back together, and I'm going to do another demonstration that might surprise you. So, give me a moment. All right, here it is. The Van de Graaff back in action. So, all right, here we go. Daredevil Tupaj. $360,000 volts. All right, so how am I not dead? 120 into the socket kills me. I just took 360,000 in my fist. And you should know the answer to this, okay? Because remember, voltage is the ratio of the thrust per charge that a single electron gets. If I take a single electron at a zillion miles an hour, whap, hits my hand, that one electron has maybe millions of volts, and it's one electron. Okay? Is it going to kill me? I won't even feel one electron, right? So the voltage is thrust per charge. The thing that I have to worry about is not just the voltage, but the available charge. Because another equation, as we said, or the same equation, I don't know if this is in the way, but maybe I'll make some room over here. Voltage is the joules per coulomb of a charge. But if I want the joules or the energy that strikes me, I need to move these two together. So I am getting 360,000 volts as thrust per charge on a single electron, and there's only a tiny bit of them on the Van de Graaff. So sure, they slam into my hand harder than if I put my hand in the socket. Then the electrons sort of hit my hand at a slower velocity. But here there's very little charge, so it doesn't kill me. If I put my hand in the socket, well, okay, it's only 120 volts. But it's hooked with wires all the way to the power plant. And so the charge that's delivered, the coulombs, is basically limitless for that given voltage. And then it keeps shocking me and shocking me and shocking me, and there's enough joules that builds up to cause more tissue damage. Okay, so that's why the Van de Graaff, I could take those sparks. Another demonstration that's popular with the Van de Graaff, I'll just show you, and I'll have to zoom out a little bit. Let's see. That should be good. Is classic demonstration, charging yourself up and allowing your hair to stand on edge. And what that shows nicely through your hair is the electric field lines with your hair. Unfortunately, I forgot and I got a haircut, so it's not going to work for me to charge myself up to this 360,000 volts, but I'll borrow a little hair here. Rabbit fur, okay? This is what we used in our electrostatics experiments, rubbing the rubber rod to charge up plastic rods, and this will now serve as my hair to stand on edge. Well, it's not as exciting as if I had rock star, 80s rock star hair. It'd be standing straight up. It'd be pretty cool. But you could see the hair sort of trying to stand on edge. Again, I'm getting to a considerable voltage, thousands and thousands of volts I am getting charged up to. I hear it leaking off, so I may have reached my limit. Yeah, I feel the hair coming back down. I'm losing the charge. So there it is, the effects of me getting negatively charged, the hair repelling. So now watch it, listen carefully. When I take my hand off and step on the floor, you'll hear my body discharge. So, see that? So I discharge. All right, so that's the Van de Graaff generator. A lot of fun. We learned some things, how we could do actual calculation with our analysis, some interesting things about the voltage, and what we're going to do in the next time we're going to do the Van de Graaff generators again, and I'll show you some other interesting things, how we can discharge the Van de Graaff generator with sparks and some other cool things with the Van de Graaff. All right, I hope you enjoyed this video. I'll see you in the next physics video.